Hello everyone. In the previous video we discussed one of the application of flip-flop, that is shift register. So continuing that, in this video I will be discussing one more application of flip-flop, that is counter. So let's see what is counter. Counters are important digital electronic circuits. They are sequential logic circuits because timing is obviously important and they need a memory characteristics. And a counter is defined as it is a group of flip-flops which is used to count the number of clock pulses. And these digital counters have some of the following important characteristics. They are: first one is maximum number of count. So this is a very important characteristics because the number of flip-flops required to design counter is decided by the maximum number of count. So for example, if I want to count numbers from 0 to 7, so there are total 8 different states and 7 is the 3-bit maximum binary number. So total 8 states, so it requires 3 flip-flops. That means 2 to the power of 3 equal to 8. So if you take another example, if I want to count from 0 to 15, there are total 16 different states. 2 to the power of 4 equal to 16, hence it requires 4 flip-flops. So that means the number of flip-flops required to design a particular counter is decided by the maximum number of count. That is the first characteristics. And second one is up down count. So counter, you can design it for up counter or we can design it for down count. And third one is asynchronous or synchronous operation. So if you consider the counters, there are two types of counters. One is asynchronous and another is synchronous counters. In synchronous counters, all flip-flops are triggered with same clock simultaneously. But in case of asynchronous counter, different flip-flops are triggered with different clock but not simultaneously. That is the main difference between synchronous and asynchronous counters. And fourth one is free running or self-stopping. So these are the important characteristics of digital counters. So next one, asynchronous or ripple counter. Asynchronous counter are commonly referred to as ripple counter because the effect of the input clock pulse is first felt by the first flip-flop, that is FF0, and it cannot get to the second flip-flop immediately because of the propagation delay through FF0. So the effect of an input clock pulse ripples through the counter, taking some time due to propagation delays to reach the last flip-flop. Hence, asynchronous counter is also called as ripple counter. So that means in asynchronous counter, only the first flip-flop receive clock pulse from the source, that is clock generator, and other flip-flops receive clock pulses from either Q or Q bar of prior flip-flop. So next one is 3-bit asynchronous binary counter. This is the circuit diagram of 3-bit asynchronous binary counter, and here you can see the truth table, and this is the timing diagram of 3-bit asynchronous counter. So first, whenever we are going to design any counter, we have to decide how many flip-flops required. So here already it is a 3-bit binary counter. So 3-bit means it requires 3 flip-flops. If it is a 4-bit counter means it requires 4 flip-flops. So that means 3-bit counter means the maximum count is now 111, that is 7, because 111 is the maximum 3-bit number that you can see it in the truth table here. So now it requires 3 flip-flops, and here you can use JK flip-flop or you can use T flip-flop. So here I am using the JK flip-flop. So I connected the J and K input of the flip-flop to logic high. So that means it is acting it as a T flip-flop, because already we know that when both J and K are connected to logic high, it toggles the output. That means it acts as a T flip-flop. And this is the asynchronous counter. The only first flip-flop receives the clock pulses from the clock generator. This one you can see here. And other flip-flops receives the clock pulses from the output of the prior flip-flop. So in this case, FF1 receives the clock pulses from the Q0, that is the first flip-flop output, and FF2 clock pulses received by the output of the FF1 flip-flop, that is Q1. And this is the up counter. You can see it in the two table here. Q2, Q1, Q0 are the 3 inputs that you can see it in the circuit diagram here. Q2, Q1, Q0. So here Q2 is the MSB and Q0 is the LSB, that is least significant bit. So 3-bit up counter, it starts its counting from 000, 001, 010 up to 111. So after it reaches the maximum, once it reaches the maximum count, that is 111, and it rolls over to the very first state, that is 000 again. That means it repeats the counting. So let's consider the operation of this flip-flop by considering this timing diagram. So one more thing we need to observe here is, so here these all the flip-flops are negative edge triggered flip-flop. So in the previous video we discussed that if the bubble is there at the clock pin, then it is considered as a negative edge triggered flip-flop. If there is no any bubble, then it is a positive edge triggered flip-flop. So here I use the negative edge triggered flip-flop. That means the flip-flop output changes its states during negative edge of the clock pulse. That you can see in the timing diagram. So negative edge is nothing but, that is this edge, that is high to low, or you can say the falling edge or negative edge. So only during the negative edge of the clock pulse, flip-flop changes its state. Okay, let's discuss the operation of this circuit now. So initially all the flip-flops outputs are 0. That is the very first state in our truth table. This is when there is no any clock pulse, that is initial state. So when you apply the clock pulses for the very first flip-flop, so this flip-flop changes its state only during the negative edge of the clock pulse, that you can see here, the very first negative edge of the clock pulse here. So the Q1 will changes its state from 0 to 1. Here you can see, because J and K both are connected to high. Already we know that in JK flip-flop, if both J and K are high, the output toggles. Toggle means if the previous output is 0, then it becomes 1. If it is 1, then it becomes 0. So now here output is 0, so now it toggles to 1. Right? Now what about the FF1 and FF2 flip-flop? Because the only first flip-flop receives the clock pulses from the clock generator, but for the FF1 flip-flop the output of Q0 is connected. So now Q0 output changes from 0 to 1. So 0 to 1 is nothing but it's a positive edge, right? So I told, right? So this is the positive edge in the clock pulse, that is from 0 to 1. Negative edge is nothing but 1 to 0, that is falling edge. Positive edge is nothing but 0 to 1, that is leading edge. So now here 0 to 1, so it's a positive clock pulse or positive edge. So the flip-flop will not active because the flip-flop only changes its state during the negative edge. So here now it's a positive edge, so the flip-flop will not changes its state, so it retains the previous state, that is 0 only. So again here you consider the output of Q1 is connected to the clock input of the FF2. So here the Q1 it retains its state 0 only, hence the FF2 also retains its previous state because it is not receiving the negative edge of the clock. So now Q2 is 0, Q1 is 0, Q0 is 1. So that is the second state, that is in decimal its value is 1. This is after the first negative edge of the clock. Let's see during the next negative edge of the clock. So next negative edge of the clock is here. So negative edge of the clock means again this FF0 changes its state from 1 to 0 now. That means it toggles the output. Right? So now the Q0 output is 0. So what about the output of FF1? So now the state 1 to 0. So 1 to 0 is nothing but it's a negative edge. So now FF1 changes its state. That means it changes its output from 0 to 1 now. And next, so here the transition from 0 to 1. So 0 to 1 is nothing but it's a positive edge. So FF2 will not change its output. So it retains its previous state, that is 0. So now output is 0 1 0, that is the next count. That is, you can see it in the timing diagram. So for the second negative edge, so Q3 is 0, Q2 is 1 and Q1 is 0. Okay, so this is Q2, this is Q1 and this is Q0. Okay, so for the next negative edge, again this FF0 changes its state from 0 to 1, and now here 0 to 1 transition, that is positive edge, so the output of FF1 will not be changed, so it retains its previous state, that is 1. And again here FF2 is not receiving the any negative edge because here one to one transition is there, so it retains its previous state, that is 0. So now the next state is 0 1 1, so that is 3. So for again next negative edge of the clock, so ff naught changes its state from 1 to 0. So 1 to 0 means ff1 also changes its state because now it's a negative edge, so it's changes its state from 1 to 0. So now what about the output of ff2, because here the transition is 1 to 0, so 1 to 0 is nothing but it's a negative edge, so the q2 changes its state from 0 to 1. Now the output is 1 0 0, that is the next state. So like this it changes its state every time depending on the negative edge of the clock pulse. So once it reaches the maximum count, that is 1 1 1, let's see what is the next state. So after the 7th clock pulse the count value is 1 1 1 1. So for the 8th clock pulse the next count value should be 0 0 0 because this is the maximum 3-bit value. So let's see whether we'll get the 0 0 0 or not. So for the next negative edge, it's the first flip-flop changes its state from 1 to 0, right? So now here 1 to 0 is nothing but it's a negative edge, so this ff1 also changes its state from 1 to 0, and again 1 to 0 is it's a negative edge, hence this ff2 output also changes its state from 1 to 0, hence we'll get the output 0 0 0, that is the very first states. So from here it repeats its count values. So this is how the 3-bit asynchronous up counter works. So here one more thing we need to observe is, so it's a 3-bit counter, there are total 8 states, that is from 0 to 7. So that means the number of states are 8 but it requires 7 clock pulses, right? So that means if to count the n number of states it requires, for example, okay, if n is the 3 that is 3-bit counter, so it requires 2 to the power of n minus 1, that is 2 to the power of 3 is 8 minus 1, that is 7 clock pulses requires. That means for n bit counter 2 to the power of n minus 1 clock pulses requires. That's it. So next 4-bit asynchronous binary counter. So the working of 4-bit asynchronous up counter is similar to 3-bit, but here now it's a 4-bit, so it requires 4 flip-flops and the total number of states are 16, that is from 0 0 0 0 to 1 1 1 1, total 16 different states, and 4-bit means 2 to the power of 4 minus 1, that is 16 minus 1, 15 clock pulses requires to count the all the states. You can see here for the 16th clock pulse again it repeats. So here again I use the negative edge triggered JK flip-flop, and the working is similar to whatever we discussed in the 3-bit asynchronous counter. So next one, asynchronous decade counter or mod 10 counter. The modulus of a counter is the number of unique states that the counter will sequence through. Counter can also be designed to have a number of states in their sequence that is less than the maximum of 2 to the power of n. So here modulus counter is nothing but, so if you consider the any counter, previously we discussed the 3-bit and 4-bit asynchronous counter. So there the maximum number of counts are 2 to the power of n. In the case of 3-bit, 2 to the power of 3 is 8. So 8 different states. In 4-bit counter, 2 to the power 4, total 16 states. So those are the maximum number of counts. But in modulus counter, you can design the counter to count the less than the maximum number of count states. So counters with states in their sequence are called decade counters. So one way to make the counter recycle after the particular count. For example, if you consider here mod 10 counter, so that means it has to count only 10 states, that is from 0 to 9. So after 9 again it has to repeat its count. That means after 9 we should not get the 10, that is 1010, but we should get the 0000. So that is the meaning of the mod 10 counter. For example, if I consider the mod 6 counter, so it has to count from 0 to 5. The next state 6 should not count, so the next count should be 0 only. So that is the meaning of the mod counter. So here mod 10 counter, so it has to count from 0 to 9. So 9 is nothing but in binary, how do you write 1001? So to represent the 9 it requires 4 bits. So it requires 4 bits, means to design the mod 10 counter it requires 4 flip-flops. But how do you design a counter? It has to count only from 0 to 9. After 9 the counter value becomes 00. So there is some slight modifications we have to do it in the circuit. That one we'll see. One way to make the counter recycle after the count of 9, that is 1001, is to decode count 10 1010 with a NAND gate and connect the output of NAND gate to the clear inputs of the flip-flops. The inputs, the NAND gate, are from the Q output from the FF1 and FF3, because here in the after 1001 the next state is 1010. So here Q output from the FF1 and FF3, that one we'll see it in the diagram here. Okay, so this is the FF3 and this is the FF1. Yeah, here you can see here FF3 and FF1, both the values are 1. So connect the output of FF3 and FF1 to the NAND gate. So output of NAND gate connect to the clear input of the all the flip-flops, hence all the flip-flops will be cleared or reset to 0. That one we'll see it in the circuit diagram here. This is the mod 10 asynchronous counter, and this is the truth table. So Q3, Q2, Q1, Q0. Q3 is the MSB here and Q0 is the LSB. So total there are 10 state, that is from 0000 to 1001. So after this 1001, the next state is 0000. So the working is similar to the what we discussed in 3-bit asynchronous counter. So let's see what happens after 1001. So here we can write this is Q3 is 1 and this is 0 and this is 0. Okay, now the current state of the counter is 1001. So for the next negative edge of the clock, what happens? We'll see. So for the next negative edge of the clock, the very first flip-flop, it toggles its output from 1 to 0, right? And now here 1 to 0 transition, so that is again its negative edge. So here FF1 also changes its state from 0 to 1 now. And now 0 to 1 is it's a positive edge. So FF2 will not change its output state. It retains its previous state, that is 0 only. And again here there is no transition. It retains its previous value, that is 0. Hence this FF3 will not change its state. It maintains its previous state, that is 1. But as soon as it changes its output, you can see it here. So here 1 0 1 0. So here this 1, the output of FF1, that is Q1, is connected to the NAND gate, one input of the NAND gate, and the output of FF3, that is Q3, is connected to the another input of the NAND gate. So already you know that if all the inputs of NAND gate are high, then the output becomes 0. So now the output of this NAND gate is 0. So this output of NAND gate is connected to the clear input of all the flip-flops, and these clear inputs are active low. So active low means to clear the flip-flop we need to provide the logic low signal. So that logic low signal we are getting at the NAND gate output. So that is connected to the all the clear input of the flip-flops. So now all the flip-flop value becomes 0. That means it resets all the flip-flops. Hence after 1001 you will not get the 1010 state. So after 1001 immediately we will get the 000 value. So this is how we can design the mod 10 counter. So let's consider one more example, mod 6 counter. So as I already told that mod 6 counter means it has to count from 0 to 5. And how do you represent the 5 in binary? By using 3 bits, 1 0 1. That one you can see here. 101 is the binary equivalent of 5. So by using 3 bit we can represent 5 in binary, hence it requires 3 flip-flops. Mod 6 counter requires 3 flip-flops, and here A, B, C are the outputs. Here C is the MSB and A is the LSB, as you can see here, C, B, A. And here this is the present state and this is the next state. So present state is nothing but, for example, if I consider the initial state value 0 0 0. So this is the present state. So whenever the first flip-flop receives the negative edge of the clock, so the next state is 0 0 1. So that is the first flip-flop changes its output from 0 to 1. So here 0 to 1 is nothing but it's a positive edge, hence the second flip-flop will not change its output. It retains the previous value, that is 0, and here again there is no any negative transition. So the third flip-flop also it retains its previous value, that is 0. So 0 0 1 is the next state, right? So again for the next negative edge, the first flip-flop changes its state from 1 to 0, and now 1 to 0 transition, so that is it's a negative edge, hence this second flip-flop it changes its state from 0 to 1, right? And third flip-flop, here 0 to 1 transition is nothing but it's a positive edge, hence this third flip-flop will not change its output state, it retains its previous state, that is 0. So now the output is 0 1 0. So that is the next state here. Previous state was 0 0 1. So now output is 0 1 0. So again for the next clock pulse we'll get the 0 1 1, and after this we'll get 1 0 0, and after this we'll get 1 0 1. So this is the mod 6 counter. The maximum count value is 101. So after this count value 101, we should get the 000. We should not get 110. So after 101, the next value is 6, that is 110. So let's consider. So for the negative edge of the clock, so it changes its state from 1 to 0. So now 1 to 0 means it's a negative edge, hence the second flip-flop changes its state from 0 to 1. So again 0 to 1 is it's a negative edge, so the third flip-flop changes its state from 0 to 1. 0 to 1 it's not a negative edge, it's a positive edge, hence the third flip-flop will not change its states, it retains its previous value, that is 1. So now the count value is 110, but once the output is 110, you can see here I use the NAND gate here, the output of the second flip-flop, that is because the second flip-flop and third flip-flop's output are 1, so I have to consider those two outputs and connect it to the NAND gate. You can see here the output of the second flip-flop connected to one input of this NAND gate, and the output of this third flip-flop, so that is connected to the another input of the NAND gate. So now the output of this NAND gate becomes 0, so that is connected to the clear input of the all the flip-flop. So this is the clear input. So now clear inputs are active low input, so the NAND gate output is 0, hence all the flip-flops resets, hence all the flip-flop output becomes 0 0 0. So this is how we can design the mod 6 counter. So here the only thing is we need to consider wherever the outputs are 1, so consider those outputs and connect it to the NAND gate, and the output of that NAND gate is connect it to the all the clear inputs of the flip-flop. So for example, if I say to design mod 3 counter, so mod 3 counter means it has to count from 0 to 2, that is 0 0 0 0 0 1 0 1 0. So after 0 1 0 we should get the 0 1 1. So that means here you can see we should not get this 0 1 1. So in this state consider ones. For example, here the output A and B are 1 1. So A is here and B is here. That means the output of the first flip flop and second flip flop are high. So consider these two outputs connected to the NAND gate and the output of NAND gate connected to the clear input of the flip flop. So this is the how you can design the mod counter.